Assalamualaikum and good afternoon. So today we're going to still discuss on the previous topic, which is simple linear regression. But what we're going to do today is we're going to focus on one particular test on simple linear regression, which is called as the linearity test. So you guys can hear me, right?
Yes.
Yes, miss.
All right. Thank you. Thank you so much. Okay, so what happened here is that, first of all, I'm going to explain to you what is the linearity test. So basically, there is a test with this particular, what I call the null hypothesis. So we are testing whether beta 1 is equal 0 or beta 1 is not equal 0. So the idea is going to be pretty much similar as what we have discussed in chapter 3. So whereby whatever that goes with an equal sign goes to the H null, and whatever is unequal will be on the alternative. So what does beta 1 equals 0 or beta 1 is not equal 0 actually means? So in words, it actually means that when beta 1 is equal 0, so it means that there is no relationship between our variable x and also y. And when beta 1 is not equal 0, it could be a positive value, it could be a negative value. So that means there is a relationship between our variable x and also y. So why is when beta 1 equals 0, no relationship? Beta 1 is not equal 0, there is a relationship. So this is because of the nature of the model itself. So if you remember, I did mention to you before, this is called a simple linear regression because our model is actually adopted from the simple linear, the linear equation that we have seen before, y equal mx plus c. So basically our equation is y equal beta 1x plus beta naught, and this actually imitates the equation of straight line of y equal mx plus c. So where the gradient is going to be given by the value of beta 1, and this y-intercept is going to be given by the value of beta naught. So basically what is beta 1? So beta 1 is actually the gradient of the straight line of our model itself. Okay, when we talk about gradient, so gradient, it could be positive, it could be negative, and it could also take a value of 0. So this is an example of a positive gradient. So it looks like this. So this is a positive gradient. So what does it mean by a positive gradient? So positive gradient means when we go towards this side, so the graph is actually increasing. So that is what it means by having a positive gradient. So when x is increasing, y is increasing as well. So when you have a negative gradient, so what happens is that the relationship will be the opposite, for which when the value of x increases, the value of y is going to decrease. So that is what it means by having a negative gradient. And instead of having a positive and negative gradient, so having a zero gradient is also possible. So what does it mean by having a zero gradient? So therefore, your gradient is going to look like this. It's going to be a horizontal line. So the thing about having a horizontal line as a gradient is that, so no matter what value do we pick for x, the value of y is always going to be the same. For example, here, so if I would choose the value of x is equal 1, so what is going to be my y value? So my y value is going to equal 2. And even if I were to pick the value of x equal 2, so what is going to be the value of y? So the value of y is still going to equal 2. So meaning by the value of x doesn't change the value of y. So the value of y is fixed. No matter what is going to be the value of x, the value of y is still always going to be the same. And in other words, what happened is that, so there is no relationship between x and also y. So that is why when we do the test, when beta 1 is equal 0, so when the gradient is equal 0, so there is no relationship between x and y. When beta 1 is not equal 0, when the gradient is not equal 0, it could be positive or negative. So there is a relationship between x and also y. So when you write your hypothesis, when you do test of linearity, there are two ways of writing this. So whether you want to write it in terms of symbol, so which refers to this part over here, or you want to write it in terms of words, which is going to be in terms of what you have over here. But of course, when you write it in terms of words, so you have to substitute what is your x variable and what is going to be the y variable, so according to the problem that we had. Okay, so that is why it's beta 1 equals 0 and beta 1 is not equal 0, because of that. Okay, how to do the linearity test. So if you have watched the video, so you should know that there are actually 3 ways of doing linearity tests. So the first is going to be using the t-test. How do you use the t-test? So you're going to be finding the test statistic by using the formula that is in your statistical table. So this is your statistical table. So there is this particular column that says hypothesis testing for beta 1. So how do you find the test statistics? So this is the formula for the test statistics. This is the formula for the t-test, so it's here. So that is if you want to use the first method, so which is by using the t-test. So this will be the similar idea to what we have discussed in chapter 3. So that will be the idea of how to use it, the t-test. Again, second way of doing the linearity test, you can also use the ANOVA table. So remember what we have discussed in ANOVA for chapter 4. So when you use ANOVA table, when you calculate the mean square of your treatment, divide by mean square of the error, you will get the value of the f-test. And the idea of doing the test is going to be very similar to what we have done in chapter 4. Okay, and the last way of doing the test is by using p-value. And when we talk about p-value, so actually it is possible to find p-value by using your calculator, but the way to do it is going to be extremely super complicated. And for this case, is it possible? It is like almost impossible for you to do linearity tests by having the p-value by using the calculation by hand. So it doesn't make sense. So if you get a p-value, so it must have been from the software. And of course, for our course, for this particular course, we are using Excel. So the p-value, if you want to use the p-value, so what happened is that you will be given an Excel output. So from the Excel output given, so you extract the p-value and then you can do the test. So what is going to be the procedure to do the linearity test? The procedure is going to be exactly the same as what we have seen in chapter 3, as what we have seen in chapter 4. So this is just simply hypothesis testing. So step number 1 is going to be conducting the hypothesis. So not conducting, but writing the hypothesis. So the hypothesis is fixed. So it is always going to be beta 1 equals 0 or no relationship for the null hypothesis. And for the alternative hypothesis, it is always going to be beta 1 is not equal 0. So which actually means there is a relationship between x and also y. And of course, after you have written the hypothesis, so now you're going to decide whether or not you're going to reject the h-null. And how are you supposed to do so? So by using any of the 3 methods that's stated over here. Okay, so depending on what's given, what information is given in the question, so what the question actually asks for, so you're going to decide what method I'm going to use in order to reject or do not reject h-null. After this, I will explain to you in detail. So what is the difference between all these 3 methods? And after you have decided whether you're going to reject or do not reject, of course, the last step is going to conclude. So you are going to conclude so whether there is a relationship between x and y or there is no relationship between x and also y. So that is the last step. Okay, now let's have a look at all the methods individually. So just for you to get a clearer idea of what you're going to come across later. So method number 1 is by using the t-test, as I mentioned before. So how do you calculate the test statistics, so which we call as t-test over here? So by using this particular formula over here, and this particular formula you can find in the statistical table. So basically this is on page number 9. So written over here, so refer full formula in page number 9. Okay, so for a t-test, what component do you need? You're going to need what is going to be the beta 1 value. So that is beta 1 value. And for this one, so this is actually going to be 0 all the time. So that is why this is beta 1 equals 0, because this value actually comes from the hypothesis. Remember, the hypothesis is given by, so beta 1 is equal 0, and null is beta 1 is not equal 0. So if you recall in chapter 3, for formula, we have mu minus mu naught. So basically, this is the naught. So that is why for this case, it is written by a value of 0. So therefore, this beta 1 is going to be a value of 0. So that is why when you simplify, the formula simply become beta 1 hat. So beta 1 hat is actually the value of beta 1. And at the bottom, so this is going to be divided by the standard error of beta 1. So sometimes in the question, they could actually give you right away. So what is going to be the value of a standard error of beta 1? So you don't have to do the calculation. You just take the value and calculate, and that's it. Okay, however, so there are also certain cases that they don't give you this particular value. So what you have to do is, so you have to use this formula. That standard error of beta 1 is given by mean square residual, so multiplied by 1 over sum of xx. And what is going to be the formula of mean square residual? So down here, so that is a particular formula for that. So mean square residual is given by SYY minus beta 1 hat SXY over n minus 2. So you have to use this formula, substitute in here, and then only you will able to get the value of the standard error of beta 1. So it depends on what is being given in the question. If this one is already given, then no need to calculate. But if it's not given, so then you have to calculate the whole thing in order for you to find the value of the t-test. So that will be the idea of the t-test. And how do we decide so whether we are going to reject or do not reject? So if you remember what we have discussed in chapter 3, so how do we decide whether it's going to be two tail, one tail, or so it's going to be two tail, left tail, or right tail? So that is depending on the symbol in the hypothesis. For this case, we have hypothesis of beta 1 equals 0 or beta naught is equal 0. So this is, if you remember, this is a characteristic of two-tailed test. So that is why over here, so we are going to have a two-tailed test for the rejection process. Okay, and when we have two-tail, automatically your alpha value is going to be divided by 2. So basically, this is going to be your critical value. So you're going to have two critical values, one on the left-hand side, one on the right-hand side, because we have two rejection regions. Okay, for the critical value, so on the right-hand side is given by T alpha over 2n minus 2. On the left-hand side is going to be exactly the same value. You only have to negative that. So it's going to be negative T alpha over 2n minus 2. And of course, so if your value, when you compare with the t-test, if it falls into the rejection region, you reject. If it falls into the acceptance regions, you do not reject. Again, I would like to remind you, so when you decide whether reject or do not reject, please use term reject or do not reject H not H now. Okay, so do not use accept H alternative. So basically, I know you that what you actually means is correct. So you reject H now, so you're going to accept H alternative. But statistically, so that thing is actually wrong, because you have to remember, so when we do any test, so it is done on the null hypothesis. We don't really give a damn about H alternative. So that is why you have to state reject or do not reject the H null. So please do not use the term accept H alternative. I come across that quite a number of you are using that for the ANOVA. So that is statistically a wrong term for you to use. Okay, so basically on the two-tailed test, so that is how you're going to decide whether you're going to reject or do not reject when you're using t-test. And then after you're done with that, you are going to come across with the conclusion. So what is going to be the conclusion of that? So that is going to be the first method, which is t-test. Okay, the second method will be called as the ANOVA table. So how do you construct the ANOVA table? It will be exactly the same idea as what we have seen in chapter 4. So if you understand what you have done in chapter 4, so this ANOVA table is going to be a piece of cake for you. But of course, the formula is going to be a little bit different. The difference is only going to be here on how do you find the sum square regression and also the sum square residual. Okay, for the case of sum square regression, so the formula is given by beta 1 hat sxy, and for the sum square of residual, it's given by syy minus beta 1 hat of sxy. So that is the formula on how do you find the sum of squares for regression and sum of square of residual. And of course, sum square total, so that is going to be given by syy. All you have to do is find syy and put it there. So that is going to be your sum square of total. And then in terms of the degree of freedom, so this is fixed. So the regression, the degree of freedom is always going to be 1. So it's always 1. It's not going to be any other value. So residual, it's counted by having n minus 2. So you know what is n. N is going to be our sample size. And for the total, degree of freedom is given by n minus 1. Okay, and then how do you find mean square? So how do we find mean square for this ANOVA table is the same as what you have done in chapter 4. So how do we find mean square? So it's going to be sum square divided by degree of freedom. So that's what's happening over here. So you take this value, so you divide by 1, so you will get the mean square for the residual. So you take this value, sum square residual, you divide by n minus 2, so you will get the mean square of the residual. And of course, our test statistic is going to be given by f-test. How do we calculate the f-test? You take the value on top, divide value at the bottom. So that is going to be your value of f-test. But the only drawback is, so after you have found what is going to be the f-test, so you are going to need to find what is going to be the critical value. And for this case, the the critical value, it will be the same idea as ANOVA. So it's going to be f alpha 1 and n minus 2. So 1 comes from here, and n minus 2 comes from the column right beneath it. Okay, so that is going to be the critical value. And remember, if you did a right tail test for ANOVA, so So it's going to be the same for this case as well. It is also going to be a right-tailed test. So meaning by, if you compare with the value of f test, and if it falls into the rejection region, so you reject. If it's fall into the acceptance region, then you do not reject. So that is how you decide whether you reject or not. Okay, so that is going to be the second method, so which is called as the ANOVA table for test of linearity. And the last way is p-value, so which come from Excel output. So when you do simple linear regression by using Excel, so this is kind of like the output that you're going to obtain. And I'm pretty sure that there's one particular topic in chapter 5 that they actually talk specifically about the Excel outputs for simple linear regression and multiple linear regression. And I expected you to already have listened to the video, so you should be very clear what information are being given in this particular Excel output. So among the most important output will be here. So this multiple R. So this multiple R is actually your small r. The small r, if you remember. So what is the small r? What does small r stands for? Can anyone tell me? What does the value of small r stands for? So what is that? Your Cambridge value said it's going to be correlation coefficient. That's correct. So R actually stands for correlation coefficient. Okay, and then we also have R square right underneath it, and we know that R square stands for this one. So this is going to be the, what do you call that, the symbol, and it stands for the coefficient of determination. So I did mention to you previously in the previous lecture, when we interpret for correlation coefficient, there are three things that you have to mention. First, so whether it's going to be strong, moderate, or weak, so that is called as the strength. And then you have to mention the position, whether it's going to be positive relationship, negative relationship, and then you have to mention the word linear, because this is a linear model, because the model actually is not restricted to only linear. So in statistics, there are a lot of models. You can have quadratic model, you could have a 2 power of 5 model, and so on. But for this particular one, we're talking about linear model. So that is why it is important for you to have the linear word. And then we also have a coefficient of determination, R square. And I did mention to you before also the fact that when we describe R square, so your answer has to be in terms of percentage. So express it in terms of percentage, right? So the percentage of the variation in Y can be explained by X. So that is the interpretation. So adjusted, we're not going to use this yet because adjusted will be for multiple linear regression. So that one we'll discuss in the lecture next week. Okay, and then we have a bunch of things over here as well. Among the most important things is going to be right here, the coefficients. So this coefficient actually give you the value of beta naught and also beta 1. So during the previous lecture, we already done the calculation by hand. So how do you calculate for beta naught and beta 1? Actually, you can also use your calculator to find beta naught and beta 1. So does that mean that you can simply put the values into your calculator and write, oh, beta 1 is going to equal this value? The answer is no. You still have to do the calculation, but you can actually check whether your value is correct or wrong by using your calculator, because not all calculators are capable of doing that. So we don't know what calculator are you using. So just to be fair to everyone, so you still have to do the calculation by hand, but you can actually check the value using your calculator. So at the top over here is going to be the intercept. We know the value that is related to the intercept is going to be the beta naught. So up here is actually a value of beta naught, 26.8926. And the value of underneath over here is going to be related to x. So this is actually the gradient, so which is going to be the beta 1. So those are among the values that are very important in Excel output when it comes to simple linear regression. And of course, so the other one that is our main focus today is going to be this ANOVA table. So it is in between the table that we have the value of intercept and all, and the top table right here. So it's the middle table. So what happened is that when you do ANOVA in chapter 4, so the last column will give you the value of the critical value. The significant F actually give you the value of critical value, but that is not going to be the case for simple linear regression. Instead of giving you the value of the critical value, it actually gives you a p-value. So when you do the test, this is going to be the p-value that you're going to use for the linearity test. And there are actually two places where the value is given. First, on the ANOVA table. So this significance F value, and it is also written over here. So under the P value, so this is actually P value for beta naught. So this one is actually the P value for test of beta 1, so which is our test of linearity. So both of these two are going to give you exactly the same answer because they are exactly the same P value. Okay, so that is a summary of the Excel output for the simple linear regression. And if you remember the rule, so what is the rule for using p-value? So when you have a p-value, so that is less than alpha, so what happens is that you're going to reject the h-null. When you have a p-value which is greater than alpha, so what you're going to do is you do not reject h-null. So if you ask me, I always prefer to use p-value over f-test or t-test because I don't have to bother with the critical value. So I don't want to go and find a critical value in the book. I can simply compare that with the alpha value. It's going to be easier that way. So if the question doesn't state what method to use, you actually have a choice. So your option, the best one should be the p-value. And this is what I mentioned just now. Please do not use the term except h. This is not h null, so it should be except h alternative, except h1. So that is actually a wrong term. You don't really use except h alternative. Okay, so that is going to be the three methods that we're going to have a look at. So now let's have a look at them in terms of questions. How is it being asked? So let's have a look at this question. So the first one. So it says over here, in Department of Educational Psychology and Counseling, University of Harimau Malaya. So a researcher noted that people have more difficulty to sleep in a bright room than in a dark room. So what happened over here is that what is being studied? So we're going to study the relationship between the intensity of light and time taken to fall asleep in minute for people. So he took a sample of 12 staff from the university. So we have two information in one particular sentence here. So one is this particular particular statement, relationship between the intensity of light and time taken to fall asleep. So it's actually giving us a hint what are the variables. So what is going to be the x and what is going to be the y. Okay, and the second information that we have is going to be regarding this. So the fact that we have a sample of 12 staff, so meaning that our value of n for this case, n is going to equal 12. So then we have all the data for the sample that we have taken is recorded over here, so you don't have to do any calculation. So all the value of sum of x and sum of x squared is already been given. Okay, the thing is that what happened if you were given a bunch of data? So this is going to be x, this is going to be y, and you don't have the sum of x and the sum of x squared and so on. So how do you find that? That is by using your calculator. I did mention this to you before. In the previous lecture, I said, so if I'm pretty sure that the lecturer who gave you a video on this particular topic should have mentioned to you about how it is being done, but if they don't actually give the what do you call it, a detailed step on how to do it, so please let me know so I can actually make you a tutorial on that. But I think that they actually give you a detailed step in the book as well, so please check that. So have a look in the book first. So try to figure out on your own how do we actually find this value if it is not given in the question, and you have to do it by using the data given. So you have to learn how to do that. Okay, but for this one, so it is actually pretty easy because all values are already given. You just have to know how to use them. Okay, first of all, so let me ask you for this case, what is going to be our x and what is going to be our y variable? So let's start with the x variable. When you read this particular statement, so which one do you think that is going to be our x variable? So we have two variables. First is the intensity of light, and the second is the time taken to fall asleep. So among these two, so which is going to be our x independent variable?
I'm going to assume that x is the time taken to fall asleep. Y is the intensity of light.
Okay. Okay. What is x and what is y?
That's right. X,
X
Y.
depend on y or y depend on x?
Yeah. And X plus
X
X
depends.
depends on,
X depends on y.
yeah.
Okay. So here, no, it's the other way around. It's actually y depends on x. Okay.
Oh,
So when we change x, y is going to change as well. So here, does the intensity of light depend on time taken to fall asleep, or time taken to fall asleep depend on intensity of light?
time taken.
Time taken to fall asleep
Eh,
depends on intensity of light.
Exactly. So actually here, the intensity of light is going to be our x variable. So that is what we're going to vary among our participants. And because of the intensity of light, so it's going to influence how long the time taken for the person to fall asleep. Okay. So that is why for this case, x is our going to be intensity of light and y is going to be time taken to fall asleep. So remember, bear in mind, y is going to be the dependent variable. So y depends on x. Okay, so now that we have all this information, so we can answer the first question. So it says over here, so identify the control and response variable. So control is actually another name for independent variable. So that is going to be x variable. So x variable is known as control variable. It's known as predictory variable. It's known as independent variable. It has so many names. Okay, but it's actually referring to the same thing. So control variable for this case is going to be intensity of light. Okay, and the response variable for this case, that is going to be the time taken to fall asleep. So that is going to be our x and y variable. So the next question it says, so calculate the mean for the control and the response variable. So it's a very simple instruction. So all you have to do is calculate the mean. So from this information given over here, how are we going to calculate the mean? What should we do to calculate the mean? So you have this bunch of information. So which one should I use?
Y1 divided by the sample. I mean,
Uh-huh. Y1 divided by the sample?
Y1 divided by n.
Yeah, that's right. So actually, how do we calculate for mean? So when we calculate for mean, what will happen is that we sum up all the value of x. So for example, I have x is equal 1, 2, 3, 4. So what happens is that we sum all of this value. So that is going to be, in terms of symbol, we call that as the summation of x. We sum up all the value. So we divide by the sample size. So that is what we're going to do over here as well, because we are already given that sum of x is given by this and sum of y is given by this. So therefore, all we have to do is divide that by 12. So I'm going to calculate my x bar. Mean of x is going to equal 285 divided by 12. And my y bar is going to equal 308 divided by 12 as well. What is going to be the value of x bar?
23.75.
23.75. And y bar?
25.67.
25.67. It is exactly 67.
Sorry, 6667.
Okay, so it's going to be 25.6667. Remember, so when you do your calculation, please make sure that it is taken in 4 decimal places. Unless for this case, then yeah. So it only stop at 23.75. That's it. But if you have like 666667, so take 4 decimal places. I noticed this in the quiz as well, that some of you are actually using 2 decimal places. I've been reminding this to you countless times, so I don't know like how that actually slipped your mind. And remember, like in the whole calculation, if you actually use 2 or 3 instead of 4 decimal places, I am entitled to minus 1 marks from the overall total. So that is what I did. Okay, so now that I already calculated for mean, so we're going to move on to number 3. So number 3 over here is what we are supposed to do. So what is going to be the main topic I want to discuss today. So the question tests whether there is a significant relationship. When they ask you to test for relationship, this is going to be the linearity test. So between the intensity of light and time it took to fall asleep at 6% significance level. And now it specifically says over here, by using the t-test approach. So this is going to be our first method that you have to use the t-test. Okay, now, so I've actually copied the question over here so that it's going to be clear to us. And I already copied the value from up here. So instead of like putting everything over here, so I actually copied it down here as well, so we can refer to that. So now we are going to calculate what is going to be the t-test. Now let's revisit this formula over here and copy whatever that we needed. So this is going to be our t-test. So I'm going to copy this one because I noticed that just now that the value of the standard error is already given. So this is our value of the standard error. So meaning that you don't have to calculate that. you simply have to use it. So this is going to be our t-test formula. So let me put it over here for now. Okay, but the thing is that before, so we know that this is going to be 0, so this is gone. But before I want to, I can use this formula. So there are certain things that I have to calculate. And what do I mean by the certain things? I'm actually referring to this value, so which is going to be our beta 1. So if you have a look at the information given over here, so none of them is actually a value of beta 1. And we have done the calculation before. The previous lecture, I've shown you step by step on how do we calculate for beta 1. So there is a formula over here. So on how do we actually calculate for beta 1. So this is going to be how do we calculate beta 1. It's given by sxy over sxx. So let me put over here. So beta 1 is given by sxy over sxx. And all the values are actually given. So xxy is given by this value over here, so which is 1375. So this is our sxy, and sxx is given by this particular value, which is 1792.25. So what is my beta 1 value?
0.7671.
Okay, so the value is going to be 0.7671. So that is going to be our beta 1. Okay, so now that we have all the information, so we can straight away calculate what is going to be the t-test. So I'm going to put it over here. So this is my t-test. I'm going to start substituting. So beta 1 value at the top is going to be 0.7671. And at the bottom, I need to find the standard error of beta 1, which is already given. And that is 0.0047 and square root of that particular answer. So what is my t-test value?
11.1893.
11.9813?
1893.
1893. Okay, so that is going to be the value of t-test. It's given by 11.1893. Okay, so now that I have already the value of the t-test, so we can conduct the test right away. And remember, every single time the question asks you to test or conclude whether there is a significant relationship, so this is definitely going to be hypothesis testing. And bear in mind, when we do hypothesis testing, it always starts with the hypothesis itself. So write down the hypothesis first. So please do not simply write reject or do not reject. No, it's always start from step number 1, which is going to be the hypothesis. So our now hypothesis is going to be beta 1 is equal 0, no relationship. And alternative is when beta 1 is not equal 0. And our t-test we have already obtained over here. It's a value of 11.1893. But before we do the t-test, so we also need to find what is going to be the critical value. And for this case, what is going to be the critical value? Remember that this is going to be a two-tailed test. So therefore, our critical value is going to be given by t alpha over 2. And this is, I can't remember what it's going to be. I think it's going to be n minus 2. So let's refer back to the notes just now. I think the critical value is going to be given by, so it's going to be t alpha over 2. And the next parameter is going to be n minus 2. For our case, so what is going to be the alpha value? So alpha is given by 6%. So that is 0.006 divided by 2. So I'm going to have 0.03. So n minus 2. So from our from the information given, we know that n is going to take a value of 12. So minus 2. So that is going to be a value of 10. So that is going to be our critical value. And I don't have to show this to you already, like how do you find the critical value? So this is going to be from the book. It's going to be a value of 2.1202. And this is one thing that I am amazed about you guys. I don't know like where do you get your critical values? But sometimes I get a critical value with 2 decimal places. Sometimes I get a critical values which doesn't match with whatever that we have in the book. So everywhere in the statistical table, so the critical value is given in 4 decimal places. If you are referring to the statistical table, there's no way that you can get anything that is not 4 decimal places. So please, if you are actually referring to somewhere else, from now on, start using your statistical table. Okay, I don't want you to be referring anywhere else for that. We have this particular statistical table. The reason is that to make it standardized for everyone in terms of the calculation. Okay, so now I already have the critical value that is 2.1202. And because this is a two-tailed test, on the right hand side, I'm going to have a positive of this value, 2.1202. And on the other side, I'm going to have negative 2.1202. So when I compare with this value, so what does it fall into? Does it fall into the rejection region or acceptance region? Are we going to reject or do not reject this particular problem, this particular statement?
Reject.
Reject.
Okay, exactly. We're going to reject because 11 is going to fall over here because it's greater than 2. Automatically, it's going to fall into the rejection region. And in terms of like how do you argue whether you're going to reject or do not reject, I mentioned this to you before. First, either you write it in terms of inequality. So you're going to write that, okay, for this case, we don't have to compare with this one because it's going to fall on this side. If it's in between, then yes, you have to compare with both of the values. If it's false, in between, in the middle, or else you don't have to. And for this case, I'm going to write that our test is given about value of 11.1893, and that is greater than t 0.0310, so which is given by 2.1202. So therefore what happens is that we are going to reject h null. So you have two ways. So either you want to write it in terms of this inequality, or you can also write it in terms of this sketching right here. So I'm going to refer to the sketching and where does your value actually falls into. So you don't have to do both, just pick any one of them. Okay, for this case, we are going to reject h null. So what does it mean by rejecting h null? So rejecting h null means that our alternative is going to be true, that beta 1 is not equal 0. Our gradient is not equal 0. So therefore, what does that mean? There is a relationship between both of the variable. So therefore, we can write the conclusion. So at alpha equals 0.06, so there is a significant relationship. So we basically just answering the question. So it asks us to test whether there is a significant relationship. Yes, there is a significant relationship. So between the light intensity, so that is our x variable, light intensity, and also the time taken to fall asleep. Okay, so that is going to be our conclusion. That's it. So by just having all these calculations, so you will get 9 marks. And 9 marks is a lot of marks. They're almost like 1/10 of the overall marks. Okay, and the last question. So the question says that, so if you notice what happens is that the sample are taken from 12 staff from a university. So the question asks us, can the same conclusion, can whatever that we conclude, there is a relationship between x and y, can actually be implemented if the sample are university student. So can we do that? Yes or no?
Yes.
Yes. So whatever that is applied on the staff, we can also apply that on the students.
No, the number of students is more than this.
No, madam.
Okay, actually the answer is no. Okay, why is it no? Because when we do, when we wanted to conclude some, use the same conclusion, for a particular different population, that is going to be completely wrong. So if we are actually doing, I did mention this to you in the previous lecture. If our sample is actually in Malaysia and we're going to conclude the same conclusion for people who is, for example, living in Saudi Arabia, so that is not possible. So you can only use the same conclusion for the same population. So here, what happened is that in our sample, our population is actually the staff, university staff. And can we actually implement it to students? No. So that is going to be not applicable because you have to remember there are a lot of factors involved. It's going to be age, like how much intensity of work they have done during the day and so on. Okay. So basically, if the population is different, the conclusion cannot be implemented. So I'm going to write over here no. So why? Because they are different population. So because of different population. So this is going to be the reason. And I noticed that this is actually a very popular question. So I had 3 final exam questions compiled over here, and 3 of them actually asked the same thing. Can you actually implement this somewhere else and so on? Okay, so remember, so you can only implement it, the conclusion on the same population. If the population is different, automatically, so it cannot be implemented. Okay, so that is is going to be the first method, and the second method is going to be given over here. So here we have a researcher who claims that there is a linear relationship between the number of grocery stores. So we have two variables. So the first is number of grocery store and also the retail sales. So how much retail does the stores make in a month or what year? Yeah, I don't know. It's not mentioned about the timeline, so we have no idea. So we only have two variables, number of grocery store and also the retail sales in millions of selected region in Malaysia. So the data is given right here. So previously, all the calculation is done, but for this one, no calculation is done. You are only given the data. Okay, now can anyone tell me which one is going to be the X and which one is going to be the Y? Number of grocery stores, is that going to be our X or Y?
The grocery stores will be X, and then the retail sales will be Y.
Exactly. So
Yes.
number of grocery store is going to be our X. The retail sale is going to be our Y, because the number of sales is going to depend on the number of grocery stores. So question over here, set the predictor and response variable. So we have already said over here. So this is going to be our predictor. So don't worry, when I give you the answer, I'm going to write it prettily for you. But for this one, I'm just going to scribble just to make things quick. Okay, and this is going to be our response variable. Okay, so the question over here says that complete the following ANOVA table. So you're not given anything. All you're given is this bunch of data, and the question asks you to complete this particular ANOVA table. And then we're going to test the researcher's claim at alpha equals 0.01. So what does the person claim? So the person claims that there is a linear relationship between the X and also the Y variable. So that's linearity test. So when we talk about like relationship, so that is definitely going to be linearity test. All right, so how are you going to construct this table? And actually, you guys are very lucky. So this is actually a final exam question. So the students who actually have to answer this particular exam questions, so they have to memorize the formula. So what is going to be the sum square of regression? What is going to be the sum square of residual? Because it is actually not written in here. So the formula is actually not given. Okay, but you guys are very lucky because like you can actually, it's an open book, so you can actually refer to the notes that you have. Okay, and this is where you should be referring. So this is going to be our table. And so what we have to do is we're going to use this in order to find what is going to be the sum square residual and sum square regression and so on. Okay, this is going to be the formula that we're going to use. So sum square residual is given by beta 1 xy. So that is going to be our sum square residual. So I'm going to write over here. So sum square residual is given by beta 1 hat. So actually the formula is here. That's only one. Where's the residual? So residual is not given. But yeah, we can actually find that from the total. Sum square residual is given by beta 1 xy. So this is going to be our beta 1 xy. But again, so do we know what is going to be the sxy? So the answer is no. So it's not given over here. So what you have to do is you are going to find what is going to be s of xy from the information that has been given over here from the data itself. And how do you find s of xy? So we have seen this before in the previous lecture, that s of xy is going to be found by using this particular formula over here. So that is the task for you. Since I already shown this during the previous lecture, I'm not going to show this again. So I simply going to give you what is going to be the value. And I think I've calculated this earlier. And I already got that s of xy, the value is going to give me, so let me find the value first. What is the value? Okay, let me give you the value of this particular problem first. So from my calculation, so I calculated this earlier, but you do the calculation on your own. So verify whether my calculation is right or not. So I get that s of xy is going to be given by 157,261.175. So that is a large number. And I already calculated sxx as well, because you're going to need that in your calculation later. So sxx is going to be given by 519,4843.5. So those are going to be the values. Okay, so here, So we need to find SSR, sum square residual. But first, we also need to find what is going to be the value of beta 1. And according to the formula, so what is going to be the formula for beta 1? So the formula for beta 1 is going to be given by this. So it's given by SXY over SXX. So I can substitute right here. I can write that this is going to equal SXY over SXX. So multiply it by SXY. And this two, so you can multiply and put it together. I can write this as SXY squared. So divide by SXX. Now all I have to do is, so take the value that I already calculated on top. I'm going to write this as 157,261.175. So divide that by 519,4843.5. So what is going to be the value of this? So please calculate that for me. What is our sum square residual?
4,760.
Okay, for
Point
760 point.
6972.
Okay, so it's going to be 6972. Thank you. Right, so that is going to be my sum square residual. So now that I already have this value, so I can simply substitute that into our equation. Sorry, R over here does not stand for residual, but it stands for sum square of regression. So this is our formula. So SSR stands for regression. So therefore now I can substitute right here. So in my first column, that sum square here is going to be 4760.6972. So next, I also need to find what is going to be sum of square of residual. Can anyone tell me? So how do we find the sum square of residual? Like, do I have to use this formula all over again? Or what should I use if I wanted to find this column?
Minus
What would you do?
SYY with
Exactly.
regression.
That's right. So the thing is that this column over here is called as being the total. So total means when you add these two together, so you will get this value. So now that the total value is already given, so all you have to do is minus. So I'm going to have 4846. So my sum square residual is going to be given by 4846.0088 minus 4760.6972. What will be the value for that then?
85.3116.
Okay, so I'll get a value of 85.3116. So that is going to be my sum square. So now let's worry about the degree of freedom. So now that we're done with the sum square. So as we have seen in the formula before, so for the residual, so the degree of freedom is going to be n minus 2. And for the total, it's going to be n minus 1. So what is going to be my degree of freedom for the residual? So what is the n value for this case? How many n are there? How do you calculate the n? So it's not given in the question. So how do we identify how many n are there?
By the region,
Okay, how many are there
number of
then?
region, there are 8.
So n is equal?
N is equal to 8. 1, 2, 3,
Exactly.
4.
That's right. So what happened is that, so when you wanted to find if the number of n is not given in the question, as what we have seen in the previous one, all you have to do is calculate how many pair of x and y are then in there. So this is going to be the first pair, second pair, third pair, fourth pair, fifth pair, sixth pair, seventh pair, and eighth pair altogether. So that is going to be our value of n. For this case, our value of n is going to equal 8. So therefore, when I use the formula n minus 2, so it's going to be 8 minus 2, which is going to equal 6. And here I'm going to have 8 minus 1, which is equal 7. Or we know right away, how do we get 7? We just simply have to add them up, 1 and 6. And that is going to give you a value of 7. Okay? So now that I already have this value, so how do we find the mean square? So the mean square is going to be exactly the same as what you have done in the ANOVA table, in the quiz, and in your exercise if you have done so. So how do I calculate the mean square? I simply have to take the sum square divided by the degree of freedom. So here I will have 4760.6972. All right. So what about here? What about the mean square for residual? What is the value?
Sorry for
Mm.
disturb.
Mm-hmm.
May I ask some question?
Yeah, sure.
The SXY, if according to
Mm-hmm.
the formula box, we need to use the sum of x times sum of y divided by n, right?
Yeah, exactly. This is the formula.
I found different answer. I don't know whether I
Mm.
wrong or miss wrong because I calculate multiple times and then I found that seems like my calculation is not wrong.
Okay, Janine, tell me what is your value of xy? What is your
SXY,
value of sum xy? This one?
sum of x and sum of y or the total.
No. Okay, this one. Sum of xy. It's written xy in the calculator.
Oh, it got minus there.
You wouldn't get minus.
I didn't minus it. Sorry.
Oh, okay. All right. So redo the calculation again. You will get the same answer as mine.
Okay.
All right. So has anyone got the value for the mean square residual? So all you have to do is take the sum square divided by degree of freedom. What's the value for that?
14.2186.
Okay, it's going to be 14.2186. So that is going to be our mean square. And for us, in order to get the F-test, all we have to do is take the mean square at the top, divide by the mean square at the bottom. You will get a value of 334 point. So what is going to be decimal places at the back? This value is slightly different from my calculation, so it's not going to be the same. So can anyone tell me what is this decimal places at the back based on the value that we use here?
8217.
8217. Okay. Right, so that is going to be our F-test value. It's going to equal 334.8217. Okay, so that is going to be our ANOVA table. And from this calculation, you will get 17 marks. If you notice, this is not much calculation, but actually most of the calculation comes from here. So calculating SXY and SXX, it's going to be kind of long. You're going to be using this formula right here, and I strongly encourage for you to try that, unless you wouldn't know how to calculate that when the time comes. Okay, so please try that. Okay, and by filling everything, so this is going to be your ANOVA table. So next, what does the question ask for? Okay, now we're going to test. So first, complete the following ANOVA table. So that will be 12 marks. And the other 5 marks is going to be to test the researcher's claim at alpha equals 0.01. Okay, now, of course, when they say test, so this is going to be hypothesis testing. Remember, it's always start with the hypothesis. Do not skip the hypothesis. So it's going to be beta 1. It's going to be beta 1 equals 0. And beta 1 is not equal 0. So now we'll be using the second method, which is going to be ANOVA. And we get that our F-test value from the calculation is 334.8217. But we know ANOVA. So when you do ANOVA, it's going to be a right-tailed test. And of course, we also need to find what is going to be the critical value. And what is going to be the critical value for this case? So it's going to be F alpha. And for this case, we have seen that the alpha is going to be given by 0.01. And as the ANOVA table that you have done before, so the second and the third parameter comes from the degree of freedom. So which is going to be the first degree of freedom and the second degree of freedom. So it's going to be F0.0116. So that is going to be our critical value. And of course, you can simply find this by using the statistical table, and you will get a value of 13.745. Actually, the table gives you a value of 13.7450, but it doesn't matter. You can simply put 745 or 7450. So both of them mean the same thing. Okay, so that is going to be my critical value. So I can put that here. This is going to equal 13.7450. Okay, now, so if I were to compare this with my F-test, am I going to reject this or do not reject? What is going to be the outcome? What is the outcome?
Going to reject.
Exactly. So this is a very big value. So if I were to compare, it's definitely going to exceed the value of 13. So 33.4 is so much bigger compared to 13. So F-test is going to be so much bigger than F0.0116, which is equal to 13.7450. So this is going to be a definite rejection of H null. So what does it mean by rejected H null? So rejecting H null means that the alternative is going to be correct. So it's not equal 0. The gradient is not equal 0 means there is a relationship. So we're going to test the claim. So what does the person claim? So he or she claims there is a linear relationship, and that's right. So the claim is actually correct. So we can see that at alpha equals 0.01. So we have sufficient evidence to support the claim. Okay, so if you want to write more, you can write something like, we have sufficient evidence to support the claim that there is a linear relationship between the retail sale and also the number of groceries. But I'm going to stop right here. Okay, so I'm going to say just like, you know what? So we have sufficient evidence to support the claim at alpha equals 0.01. That's it. Okay, so that is going to be for this one. And okay, this two. So this two question is just asking you for the correlation coefficient. So R. So how do we calculate R? So we have seen this last week that R is calculated by using this particular formula right here. So I'll leave it to you to do it on your own. And the same goes for coefficient of determination. That is R square. And we know that when we square this value, so you will get the value of R square. So those two, I'm going to leave it to you to do it on your own. And what else? And this is equation of the estimated simple linear regression model. So that will be the same as well. So remember, our regression model is given by y is equal beta naught plus beta 1x, or you can put beta 1x plus beta naught. So that's the same. So what you have to do is basically you have to find what is going to be the value of beta 1, and you also have to find the value of beta naught. So the value of beta 1, so have we found it before, the value of beta 1? So we actually come across that. So this is going to be the value of beta 1. And then you have to do the calculation for beta naught as well. But since we have already discussed this last week, again, I'm not going to discuss this in detail. So you can do that on your own. And the last one, it says that, is it possible for the researcher to use the estimated simple linear regression? Okay, so we have this particular model. So is it possible that we are going to use the same model to predict the sale of a region with 100 grocery stores? So basically, our x is equal 100. So is our model applicable? So when we have x equal 100. So how do you know whether this is going to be a yes or no? So this will be the same idea as the population just now, remember? So this particular model, we cannot apply it for people from different population, from different region, from different calculation. But for this particular question, it asks, like, if x equal 100, can we use the model? So how do we decide? Can we use this particular model or not when x equal 100? So what you have to do is, you have to refer back to the number of x in our sample. So this is our sample. So x is going to be this value right here. So what is our smallest x value? So the smallest x value is given by 370. And the highest x value, so that is given by 2976. So can we actually use this model when x equal 100? The answer is no. Why is it the answer is no? Because when we wanted to do prediction, so we have to make sure that the number of x that we are about to use for prediction is in this particular range. Okay, but the problem is now 100 is not within our range, so therefore the answer is no. So can we use it? The answer is no, because x equal 100 is not within our range of x values. Within our range of sample values. Okay, so that is going to be the answer for this case. So I noticed that this is very popular, so asking whether or not this can actually be implemented to other cases. Okay, so that is the second method. Okay, the last method, so that is going to concern about you're being given an Excel output this time. So let's read the question first. So the question states that the manager of Yondu, so Yondu is basically a telecommunication company. Yondu is a person's name, isn't it? The manager of Yondu, a communication company randomly selected 15 customers. So basically here, our sample is n equal 15. To determine the relationship, so we have two variables. So the first variable is given by monthly data usage, which is going to be in gigabyte, and the customer's age, so which is going to be in years. So he would like to develop a linear regression model to help potential customers choose a suitable data plan, so according to their age. So figure 3 shows the regression analysis. So using Microsoft Excel with 98% confidence level. So this is actually a final exam from last semester, semester 2, 1920. Okay, so now I have two variables, so which is going to be monthly data usage and customer's age. So which one is going to be X and which one is going to be Y? Does the monthly data usage depend on age, or age depend on monthly data usage?
The data usage depends on the customer age.
Okay, the data usage is going to be Y and customer age is going to be X.
Yes.
Is that right? Okay, so that is actually correct. Okay, so this one is not very obvious. So which one depend on one? But because it could be that monthly data usage depend on age, or age depend on monthly data usage. It could be like, even if we think about it logically, it could be both sides. But how do I know that the age is going to be X and the monthly data usage is going to be Y? It's going to be because of this. Okay, so basically this is going to be our X variable. So I know that from the output itself. So the X variable is going to be given by age. So because of whatever variable that is written over here, so this is going to be your X variable. So from here right away we can tell. Okay, so customer's age is X and monthly data usage is going to be Y. So here, identify the control and response variable. So that's it. So our control is going to be the age, and our response is going to be given by data usage. Okay. So and then the question asks you to identify and interpret the correlation coefficient R and the beta naught values. I'm going to explain to you about how to interpret as well. So I'm pretty sure you already know how to interpret the correlation coefficient. So what is the correlation coefficient for this case? Where should I find the value? Where is the value? The correlation coefficient?
The R square, just square ke R.
No, it's R.
R.
Kat mana value R? Okay, as I mentioned to you just now, when I show you the Excel output in the third method, R is found here. This is your R. It's called as multiple R. Okay, so this is your R value. So for this case, our R value is given by 0.5475. Is that right? That's right. It's going to be 0.5475. Can someone interpret this for me? So the question asks you to identify. So I already identified. It's 0.5475. And then it's also asked you to interpret. Can someone interpret this for me? So how would you interpret this when you come across this in the exam? What are you going to say about this R value? So I'm going to say there is a... So what kind of relationship is this? What are the three things that I have to mention for this particular value? Okay, what is the strength for this? If I have 0.54, is it considered weak, moderate, or is it going to be strong? Which one?
Positive moderate.
Exactly. So for this case, like this is going to be positive, obviously, because this is a positive 0.5475. So that is a positive. And how do we know it's going to be moderate? I explained this to you during the previous lecture. 0.0.5 is considered as being weak. So 0.5 to 0.7 is considered as being moderate. and 0.7 until 1, so that is considered as being strong. And it applies for both positive and also negative. For example, if you come across negative 0.8, so it's going to be between over here, so 0.5 and 0.7. So that is going to be considered as being moderate. So here you have to mention that is a positive, moderate, linear. Okay, so these three things has to be there. You have to mention the direction, so the strength, and also the fact that this is a linear relationship. You will only be awarded the marks only if you have all these three words in your interpretation. So there's a positive, moderate, linear relationship between age and also data usage. So that is going to be for the correlation coefficient. And we also have to interpret the value of beta naught. So from here, what is my beta naught value? What is my beta naught value?
0.5695.
That's right. So remember up here, this is going to be your beta naught value. So underneath, this is going to be your beta 1 value because the intercept is your beta naught. So in this case, I'm going to write that. So let me put it here. So I'll write it prettily for you when I give you the PDF file. So beta naught is going to equal 0. What is that just now? 5695. Okay. So how do you interpret the value of beta naught? So what is beta naught? So we know that beta naught is going to be the intercept. So y equal mx plus c. We have y equal beta 1x plus beta naught. So basically it's going to be the y-intercept. So what is actually y-intercept? Y-intercept is the value of y when what? When?
X equals 0.
Exactly, when x is equal 0. So this is what you should include in your interpretation. So basically, when you want to interpret beta naught, so it's going to be the value of y when x is equal 0. So what is x equals 0 for this case? X actually represent the age. So you're going to say when age is 0 years, okay, so y is going to equal this particular value. But what is y? Y is going to be the data usage. So the data usage is 0.5695 gigabyte. So that is going to be the interpretation. So basically the intercept is just going to be the value of y when x is equal 0. So this is your x equals 0, age is 0. So y is going to equal 0.5695. That's it. So that is going to be your interpretation of beta naught. Okay, so this is actually what we wanted to discuss. So based on the ANOVA table in figure number 3, so this is my figure number 3. So the question asks you to refer to this particular bit, which is the ANOVA table. Test at 0.02 significant level. So my alpha value is 0.02. So whether there is a significant linear relationship between monthly data usage and customers' age. Of course, there's a relationship. There's going to be a linearity test. Okay, however, does the question ask you to use a specific method? No. The question doesn't even ask you whether you use t-test or whether you use the f-test from ANOVA, or you have to use the p-value. Of course, t-test is ruled out because we don't have the value for the t-test. So t-test is going to be out. But you have two choices right here because from this particular ANOVA table, because in question 2, they asked you to find what is going to be the value of R, S, T, and U. You already know how to do it. We already done it before. So it's going to be the same idea. So basically for this particular question, you have two choices. So either you can use the f-test from the value of U that you have obtained in the previous question, or you can also use the p-value. So you can either use this one or you can also use the p-value. But if I were you, I would definitely not going to use the f-test. The reason is that because if you want to use the f-test, you have to find the critical value. So you have to find what is going to be f of f 0.021 and also 13. R over here is going to be 13. So you have to find this in your statistical table. So therefore, if I were you, I would try to avoid that because there's going to be an easier way. And the easier way is actually referring to the p-value. The p-value has already been given. You already know that alpha is going to equal 0.02. So all we have to do is compare them. So therefore, because no method is given over here, so my option would have been the p-value. So the method is going to be the same. So my H null is going to be beta 1 equals 0. My alternative is beta 1 is not equal 0. So what happened is that my p-value from the ANOVA table is given by 0.03. So what's the value at the back? I only remember 0.03. 0.0347. That's right, thank you. So I'm going to compare that with my alpha, which is given by 0.02. And of course, my p-value is greater than alpha. So according to the rule, if p-value is greater than alpha, do I reject or do not reject? So therefore,
Do not.
reject or do not reject? If it exactly. So for this case, if it's greater, then we do not reject the H null. So what does it mean by do not reject H null? So it means that H null is actually correct, that our gradient is actually going to equal 0. So having a gradient equal 0 means that there is no relationship between x and also y. So therefore, we can say that alpha at alpha equals 0.02. So there is no significant relationship between data usage and also age. Okay, so basically those two, they have no relationship between each other. So you cannot use data usage to predict age and vice versa. Okay, so that doesn't apply for this case. Okay, so that is by just having all this written, so you will get 5 marks. So basically when you read the Excel output, you just have to know where to find those values. And I'm pretty sure if you know how to find those values, you can easily obtain the mark. So what else does the question ask for? So this is going to be pretty much the same as what we have seen previously. So this is being conducted in Malaysia. Can we actually, conclusion can be implemented if the sample in other telecommunication company in Indonesia? So the answer is going to be no. So is this conducted in Indonesia? I don't think so. So basically it doesn't say where this is conducted. So I'm going to assume that this is conducted in Malaysia. So can we use the same conclusion for telecommunication company in Indonesia? The answer is going to be no, because we have a different population, and that's it. Okay, so that is basically all the 3 methods that I wanted to discuss with you today. And I have skipped actually quite some amount of question, because I think that you already know that from our previous discussion last week. But when I give you the full calculation for this, everything is going to be there for those who have actually attempted the calculation. So you can actually compare, so which part of the calculation is not the same between us. And if you haven't, I strongly want you to attempt the question first, then only refer to the solution. The solution, I'm going to give it right away, because if I were to delay it, at one point, I'm going to completely forgotten about it. So before we end our lecture, do you have any question to ask about this particular topic? So basically, after chapter 3, so which is chapter 5, 6, chapter 4, 5, and 6, so I don't know about you, but I think that it gradually gets easier, because it's going to be something that you can actually relate to. So we do simple linear regression. Simple linear regression is actually like super famous. Like for us statisticians, we have so many methods that we can use. But for engineers especially, they have really keen interest in regression. Like most of my friends, whenever they do something with their data, they're always going to do regression. So they say that it's going to be easiest and it's going to be the most useful. So this topic is going to be very important for you. Alright, so anything else? So if you don't have anything else,
Miss, when we will be having our quiz 5?
our quiz 5, our quiz 5 is going to be on simple linear regression. We can have it next week. So
Alright.
we'll have it next week, yeah. But I will decide whether it's going to be on Tuesday or whether it's going to be on Thursday. Because next week we are going to discuss multiple linear regression and model selection. Anything else other than that? Okay, so if you don't have anything else, and I assume that you have understand whatever that we have discussed today well. So I'm going to end it here today, and next week we're going to discuss multiple linear regression and model selection. Yep.
I'm sorry to interrupt, but
No, it's
there
fine.
is someone who is asking the question in the chat box.
I didn't notice that.
Because She said.
Comment vary. How will be the implementation? Question answer is yes before we use different population. Okay, for example, like for the x value just now. So if the x value is being suggested is within our range, then yes. So it can be implemented. And conclusion is yes. If we before we use different population. Okay. How will be implementation? Question for conclusion answer is yes before we use different population. It has to be the same population then only we can implement. Let me think about it for a bit. Give me 10 seconds. So we cannot use it for different population. So we cannot use it for different timeline. For example, if we take the sample from 1990, if I want to implement it on 2000, it doesn't make sense. Yeah, basically, for example, so let's say if I were to model it, the sample is going to be for Malaysian. I can only use it for only when I want it to model Malaysians. So I cannot actually give the model to someone else from a different country and they're going to use it. It's not possible. So converse vary. So basically, like there is no way that if we have two different population, then people can actually use it. It doesn't make sense. So you only can use it when you are going to implement it on people on the same population. Okay, other than that, okay, so we are going to discuss, I mentioned just now, we're going to discuss multiple linear regression and model selection next week. So please make sure that before you join the online discussion, that you have actually watched the video. The reason is that if you come without like watching the video, so you are going to have a really hard time at understanding things. So like the reason for this online class is just for you to understand things better. So it's not like to teach you everything from scratch. Okay, so I'll leave you here for now, and I will see you next week. I will announce about the quiz later. I'll think about whether I'm going to do it on Tuesday or Thursday, and I will let you know after that. All right, so let's end here then. So I'll see you guys next week. Bye.
Thank you, Miss.
All right,
Thank you, Miss.
No problem.